Well, first, let me advertise the colloquium series that we have in Madison, and these are talks that we have every Tuesday at 10 a.m. Central Time, which is in Princeton would be 11 a.m. So please join us. It's the series which involves experts from around the world, and it's free to join. Okay. I have changed the title of my talk somewhat because initially it also included polarization, but I decided that it's better to have everything concentrated on gradients. And on this first slide, introduction slide, you see the magnetic field, which are shown by textures obtained with Rock Plus instrument on Sophia with dust polarization. And with high resolution, we obtain the structure of magnetic field with 13 CO. My collaborators are my students and my long-term collaborator, Dmitry Pogosan. During my talk, I'm going to discuss the importance of magnetic fields and all waves of the study, introduce gradient technique, discuss first initial studies with gradients, and then go to new theoretical advances and how this change our observations and obtaining magnetic field strength. So the first item is importance of magnetic fields. And I know that in the institute, there are probably not so many people so interested in magnetic fields, but I will try to make a general statement that magnetic fields are extremely important both for cosmology and astrophysics. And we have notable directions for astrophysics, which include star formation and cosmic ray physics. For foregrounds, the magnetic fields enter as we observe the polarization from early universe. And galactic synchrotron and dust radiation interfere. And we know 2014 BSEP2 polarization from the galactic foreground was mistakenly identified as coming from this enigmatic B modes. So it is important to understand what is there. Again, in the Institute, not many people do star formation, with a notable exception of Jim Stone. It is well known that for star formation, magnetic fields play a very, very important role. It was related to the classical works, for example, by Spitzer. This is the explanation how magnetic field can support the cloud. They also are important in formation of accretion disk, formation of the outflows, jets. So it is very important. Well, for the galaxies, it's very important for all stages of galactic evolution. A very important region is the galactic center, where it is challenging to study magnetic fields, but I will show how to study these magnetic fields with the new approaches. And also galactic clusters, where I will show first maps of magnetic fields. Well, what is important is magnetic fields are turbulent, and turbulence is important. I will exemplify this by considering Van Gogh's picture, Starry Night. And someone whom you surely know, namely Xiao, decided to challenge Van Gogh and to write the same picture without turbulence. So that's what she got. Well, if we are talking seriously, for star formation, there are numerous studies which show how important turbulence. For example, on the picture from Krumbol's and Federer's paper, the structure of floors. So these are hydro floors are shown for the same level of turbulence, but in the presence of magnetic field and without magnetic field. Incidentally, together with my former student, Andrei Berezniak, we published 2 years ago a book on turbulence in magnetohydrodynamics. And there are many there is an extensive discussion of properties of turbulence in the presence of magnetic field there. What is important in terms of magnetic fields is the level of magnetization. How can we characterize this magnetization? Magnetization we can characterize as the level of disturbance of magnetic field. And it can be characterized by Alphen Mach number, which is analogous to sonic Mach number, but for magnetized media. This is injection velocity to the Alphen speed. And if the Alphen Mach number is low, magnetic fields are slightly perturbed. And if you increase the Alphen Mach number, your magnetic fields are becoming more and more perturbed. So for astronomical, astrophysical, and cosmological problems, we need to know about magnetic fields. We want to know the direction of magnetic fields. As I discussed earlier, we want to know the magnetization of media given by Alphen Mach number. We would like to know the magnetic field strength, and we would like to know the three-dimensional distribution of all these characteristics in various media, in various, for example, phases of the ISM. My interest to magnetic field was stimulated by my meeting with Lyman Spitzer at the time when I was a graduate student in Cambridge, UK. And he encouraged me to work on a particular way of studying magnetic field related to polarization. And he explained to me that we are getting a lot of information through about magnetic fields through polarimetry, but we do not know how the grains are aligned. And later, with my student Hiem Huang, we suggested an analytical theory of radiative torques, which helps to understand the alignment of grains and make quantitative predictions. On the left-hand side, you see the spherical cow, our model of a helical grain. that can be aligned by radiative torques, and actually shows very good correspondence to actual radiative torques calculated, for example, by using Bruce drain DD-SCAT algorithm. But you know, it's good, but polarimetry is limited. So with my other student, Huiron Yan, we suggested another way of studying magnetic field using atomic alignment. There's this use of atoms and ions with hyperfine splitting, which can be aligned by radiation in ground or metastable state. You know, for 15 years, it was just a theoretical study. But more recently, Huiron's group in Potsdam, she's a professor there, found the evidence of this ground state alignment. And this is another way to study magnetic field. But in this presentation, I'm going to talk about a different way to study magnetic field. And this is related to use of gradients. This is my musketeers, current students who contributed to the work that I'm going to present. First of all, I would like to explain to you that this new technique is rooted in the theory of MHD turbulence and turbulent connection. What I mean? I mean that to understand how gradients work, we could consider the motion of flux tubes as shown on sub-panels A and B. What is happening with these tubes? They are being mixed up by the external forcing, and this is the dominant motion of magnetic field, strong magnetic field in magnetized turbulent media, as compared to the textbook notion of interacting Alphen waves. Why this was not considered earlier? It was not considered because when you are mixing up magnetic flux tubes, you naturally create knots. And it was not clear how these knots would behave. It was considered, it requires reconnection. And reconnection was a problematic process. But together with Ethan Wishniak, we suggested a theory of turbulent reconnection and showed that these knots will be dissolved in one eddy turnover time. Therefore, this mixing motions of magnetic flux tubes is the dominant process that allows for a connection to happen. And here I'm showing the system of flux tubes, and everywhere along this system you can have this mixing motions, and as a result, where would be the gradients? The gradients would be perpendicular to the magnetic field. So we have different types of gradients, velocity gradients, synchrotron intensity gradients, and other types, but I will be talking mostly about velocity gradients just to cover at least one theme. So let's consider velocity gradients. Velocity for this mixing motions corresponds to the Kolmogorov scaling. What other scaling do you expect if your magnetic field is not important for this mixing motions? Only Kolmogorov. So then look at this gradient. gradient is VL over L perpendicular, right? And so what you observe is that the gradients scale as scale to the minus 2/3. So what does it mean? It means that the smaller the scales we sample, the larger is the gradient. So if we do observations, we can expect that the gradients will be dominated by the motions at the smallest resolved turbulence scale. So this is a formal presentation of the gradient foundations. There was a lot of work done by Pogosan and me, which is at the basis of these studies, but we have different ways of measuring gradients. Let's consider, as I discussed, velocity gradients. So to find velocity gradients and use them to study magnetic fields, what should we do? We should use spectroscopic data, which is Doppler shifted and therefore contains information about velocities. Then calculate gradients in channel maps, velocity slices, and then turn this gradients 90 degrees to get a magnetic field. And this is as simple as that. So this is an example. This is a channel map obtained with numerical simulations. And we see these striations at this channel maps. You can say, oh, these are filaments. But these filaments are obtained with no density fluctuations. These are caustics. And you see that these caustics are aligned in the direction of magnetic field, but the gradients are perpendicular in general. But if we consider individual caustics, gradients are showing the local direction of magnetic field, local projected magnetic field direction. So as soon as we understood this, we started applying this to different problems, to different data sets. And for example, this is an old picture which shows on the right two sub-panels a comparison of magnetic field obtained with polarization, Planck data, and using Gulf H1 data. And also on the lower panels, there's this VLSC obtained magnetic field, again showed by textures obtained with 13 CO, and also with on the right side polarization obtained with the polarimetry blast pole experiment. Those who were sometime in Institute of Advanced Studies, my colleague Susan Clark stayed there, and I'm sure she discussed, for example, the filaments in channel maps, for example, for Gulf. And in her interpretation, there's a density filaments rather than caustics. However, I'm sure that she did not tell you why this density filaments are parallel to magnetic fields, and why don't we see density structures which are perpendicular to magnetic fields, and why we see this in numerical simulations, and why we have a very different ratio of these filaments, which, for example, obtained in two fluid simulations by different authors, including Inotsuka-san and Kritsuk. So our interpretation is that these filaments are caustics, and we get with gradients a high correspondence, degree of correspondence of the magnetic fields obtained with our gradient technique and polarimetry compared to the RHT technique suggested by Susan Clark. This is an example. And we actually can also produce produce the intensity of the foreground emission from that. Why I'm so confident that the most important contribution is coming from velocity caustics rather than density fluctuations, because we developed recently with my students a technique of disentangling the velocity and density fluctuations from spectroscopic data. This is the expression that we use, and we can decompose in density fluctuations and velocity fluctuations. This is a technique which is well tested with numerical data, and it was applied to H1. And in H1, we see that the contributions from velocity are more dominant, and moreover, this velocity contributions represent much better the magnetic fields when we use gradients compared to the density fluctuations. So it's also important that we unlike RHT, we do not need to appeal to any two-fluid effect, phase transition effect. For example, this is the picture of the molecular clouds, for which, as far as I know, RHT has not been applied. But we see a very good correspondence between blast ball and velocity gradient technique. Moreover, you can use different lines with a gradient technique, and therefore you can have tomography. For example, consider two lines. For example, in this case, we use CS, and CS has a lower correspondence to Planck. Is it bad or good? I think it is good, because it shows that in VLSC we have a change of magnetic field direction with density. And using different traces, we obtain three-dimensional morphology of magnetic field within the cloud. So, in addition, we are not constrained to using velocity gradients. We can use synchrotron intensity gradients, and this is the correspondence between synchrotron intensity gradients and synchrotron polarization that is obtained both applying the technique to the polarization is obtained from Planck polarization, and the intensity is also Planck intensity measurement. You see very good correspondence between the two maps. It is important that Faraday rotation does not play any role And for Planck, Faraday rotation is marginal, unimportant, but for other cases it is important, and it is good that we can obtain magnetic field just measuring intensity at one frequency. By the way, combining this with polarization, we can have a distribution of polarization direction of Faraday rotation. Well, let me go to more recent work, and it was mostly theoretical work. What I was discussing earlier was the estimates of the alignment, and it was explaining you why we are dominated by the smaller scales. But in our new work, we provided the analytical expressions for example, variance sources of gradients. If we consider, for instance, a cubical volume, we can see that the gradients are essentially coming from the contributions from the smallest resolved scales, LB. So we have this variances of differences of quantity. It could be some synchrotron intensity, for example, and it's added as a random walk fashion with the scale of your cubical cube. Well, if you want to take into account the anisotropy, as we do, in this case, we should combine the anisotropy, which is given by turbulence formula within the cube, and then add the contributions from the cubes along the line of sight. It's pretty mathematically messy, but I can show you the approximate expression for the spectrum of gradients. And using this approximate measure, one can calculate an observable parameter J, which is related to the dispersions of gradients along different axes. Where, for example, D is the structure function. So it's a limit of the ratio of the dipole to monopole component of the structure function. And this is the expression in this limiting case between this observable parameter J2 and the alpha Mach number that I told you is very essential for us to know for many astrophysical problems. Well, J2 may not be so intuitive, but consider distribution of gradients. So what we can see here, we see this dispersion of the gradients direction within some sub-block of the observational data, and it changes with the alpha Mach number, as you see. Then there is also a top to bottom ratio for this distribution. So all this can be expressed through this J2, as it's shown here. For example, top to bottom to top ratio is given by this formula. This dispersion is given by this formula. And we can also introduce polarization, or similar to polarization degree measure for the gradients. It's also observable, and this is also expressed through this J2. And I go back J2 is directly related to the alpha Mach number. So we can measure any of these characteristics and other characteristics and obtain J2, and therefore we can obtain alpha Mach number. So the gradients have significant advantages to normal polarization measurements. And for example, the measured MA, and this is very non-trivial fact, does not depend on the averaging length. For polarization, if you measure the distribution of delta B over B, measured by the dispersion of the polarization angles, in this case, you should know what is your injection state, what is the integration length. This ratio of the two is not easy to obtain, but with gradients, we are independent. And in fact, if we measure this observed delta B over B dispersion using polarization, we can find this ratio of injection state to the line of side length. So I'm not going to say that polarization is outdated, use gradients. No, we should use both polarization and gradients because there is a lot of synergy of using the two approaches. Then there is a possibility of measuring alpha Mach number and direction of magnetic fields for individual spectroscopic maps. So we can have the three-dimensional distribution of magnetization and magnetic field directions. For if we use synchrotron, in this case, we can use this distribution of magnetization and magnetic field direction as a function of synchrotron of the Faraday depth. We can also measure magnetization and magnetic fields for many spectral lines, as I already showed. We can also restore the magnetic field distribution over the image using only high spatial frequencies. For example, these high spatial frequencies can be measured by the interferometer without single dish measurements. And as I mentioned, we don't have sensitivity to Faraday rotation. So let me go and discuss some new observations and the possibility of obtaining not only magnetization, degree of randomness of magnetic field, but the magnetic field strength itself. So I can show you some study which at that time was done using empirical technique, not our formula, but what it is. It's application of gradient technique to the galactic disk. Not as, for example, was shown by Susan Clark, application to the high latitude or intermediate latitude media, but to galactic disk H1. And here we see the significant changes of magnetic field direction, which are given by these pseudo vectors. And also, this is very important, that we are measuring not only the direction, we are also measuring magnetization. And this magnetization is given by the length of this headless vectors shown. So this is our sun, and we are going out of the sun towards the specific arm and show magnetization. Well, is it possible to test whether we have a good three-dimensional plane of sky map of magnetic field? Yes, it is possible. And this is possible using starlight. Starlight polarization is influenced by this structure of magnetic field, and using this starlight, and also using the distances to the star, so okay, I should correct myself. Using our map of magnetic field and using the distances to the stars, we can predict the starlight polarization and then compare to the actual starlight polarization. This is shown here on this plot using the colors. And white correspond to perfect correspondence, and the black corresponds to anti-alignment of predicted and obtained polarization. This anti-alignment is happening in the directions of molecular clouds, because we were using only magnetic fields in H1. I also told you that gradients are only sensitive to the smaller scales. What does it mean? It means that we may use the filtering of large scales, and this resulted in a new approach. And here I show the application again to H1, and with this new filtering, we get significantly better correspondence between polarization obtained by Planck and our gradient technique. I would like to stress, unlike RHT technique, we do not have any adjustable parameters. And as you see, it's only in some particular direction where we see the differences between red vectors given by VGT and blue vectors given by Planck. And in most cases, they essentially the same. Well, I mentioned that galactic center is a very challenging region where there is a lot of physics for us to understand. With new studies, for example, using Sophia Hawk Plus, we have wonderful maps of magnetic fields of the galactic center. However, these are integrated along the side magnetic field. With the gradients, we can use different lines and get exactly magnetic field directions in different phases corresponding to the galactic center. This is very much advantageous. We can also apply the technique to galaxy clusters. And our studies, for example, of the synchrotron gradients reveal a complex structure of galactic magnetic field there. By the way, these are first magnetic field maps obtained for the galaxy clusters. In fact, also using both X-rays and synchrotron, we see both similarities and differences of the magnetic fields in different parts or phases of the galactic clusters. This is an important subject for study in itself. These applications of the technique to torus molecular cloud, and you see good correspondence with Planck, but at the same time we get not only the direction of magnetic field, but also magnetization in different part of torus. And therefore, these maps obtained with gradients are more informative compared to the polarization maps. We can measure magnetic fields in the objects where we cannot possibly measure polarization because they are so tenuous, like, for example, high velocity clouds. This is Smith high velocity clouds. And on the right-hand side are textures corresponding to the magnetic field of the Smith cloud and surrounding media, which is obtained with this with our technique. And moreover, for the Smith magnetic field, we also obtain magnetization and magnetic fields. Well, I was talking about magnetization. Is it possible to obtain magnetic field strength? Yes, it is possible. And this is the technique which we called MM2, because it uses two Mach numbers. One is Alfvén Mach number, which I described, and the another is the usual sonic Mach number. How to obtain sonic Mach number? Well, there are ways of obtaining sonic Mach number, and my previous student, Blakesley Burkett, wrote a significant part of her PhD on obtaining sonic Mach numbers from observations. Interestingly enough, however, we can use also gradients to obtain sonic Mach number. And we already use this distribution of directions of gradients, but we have another characteristic which can be used. It is the amplitude of gradients. And this amplitude, as is shown in this figure, depends on the sonic Mach number, and therefore we can obtain magnetic field strength using this new approach. And this is my last transparency, which shows the application of this new MM2 technique to Serpent's G3, G6 cloud. It was, the data was obtained with IRAM. These are dedicated studies by my student Hu Yu. And what we see here, the first is the map of Alfvén Mach number. The second is the sonic Mach number, and using MM2 technique, we're obtaining magnetic field strength. This magnetic field strength is maximal, as we expected at the densest part of this complex. So this is my summary. The gradients present a very powerful technique to study magnetic fields. And I discussed only velocity gradients and just mentioning synchrotron intensity gradients, but there are other gradient techniques. All of them are based on our understanding of theory of MHD turbulence and theory of turbulent eye connection. And as you see, we can obtain both the directions of magnetic field in different media and also magnetic field strength and magnetization. Unfortunately, I found that I cannot discuss how to use polarization in a new way. We also worked on that. This was original my plan, but I can discuss this with you during this discussion time that will be later today. Thank you very much for your attention.
Thank you very much, Alex, for the very nice introduction of this new technique. Let's answer any questions here. Wenbing?
Yeah. Oh, hi, Alex. So I want to ask about the Faraday rotation gradient. So the Faraday rotation cares about the parallel B field, whereas I think for your case, you only care about the perpendicular component of the B field, right? Because that controls the gradient in the velocity, which is perpendicular to the perpendicular component of the B field. Is there any relation between your velocity gradient map and the Faraday rotation gradient at all?
Well, you see, when we are talking about measuring velocity gradients, we are also measuring parallel velocity. Similarly, by applying this gradient technique, we find this plane of sky magnetic field direction. So if we have the distribution of Faraday rotations, we can also apply the technique and obtain the perpendicular to the line of sight direction of magnetic field. So this is something new compared to the traditional Faraday rotation, which was thought not to be sensitive to the perpendicular direction. In any case, we are using, we can use Faraday rotation similar to spectral lines and get similar information.
But they cannot be cross-tested, right? They're, because the velocity map method relies on the perpendicular, the magnetic field line information, whereas
well, in both cases we are measuring, in one case parallel to my line of sight component of velocity, and in another case we are measuring parallel to the line of sight component of magnetic field. And through the theory of turbulence, we can, using this information, we can predict and obtain the distribution of magnetic field perpendicular to the line of sight.
I see, thanks.
Jim?
Hi, Alex. Can you hear me?
Yeah.
So thanks for a great talk. And so it's really interesting to be able to measure the magnetic field, in 3D. I had a question about some of the results. For example, you had a map the magnetic field in the galactic plane over a few kiloparsecs in distance in various slices. It was sort of a third of the way back in your talk. You had sort of a movie of the directions.
I will get back to.
Yeah, sorry to make you. Yes.
No, it's fine.
So the length of the red line is the strength of the magnetic field.
Well, there are two red lines. On the left-hand side, it's the red curve, which corresponds to the slice where the magnetic field is studied. And on the right-hand side, this is the direction of magnetic field and the magnetization.
Right.
We are not to get the strength here, we can do this, but we also need to combine this with sonic Mach number, which I showed. We just simply haven't done this. We can use U again, or using the gradients amplitudes.
Right.
So we can use this no problem.
So on the right-hand side, the length of the line, the longer the line, the stronger the magnetic field.
The less perturbed magnetic field, I would say, because it could have a very different sonic Mach number. I don't know this. So it's what I was showing in the first earlier explaining magnetization. It's the level of perturbation of magnetic field.
Okay, because that sort of relates to my question, because I had thought that the stronger the field, the less it would be perturbed, and therefore, as you walk through this movie on the right-hand side, the long lines should all sort of stay lined up because they're strong fields and they wouldn't be very perturbed. But when you watch the movie, the red lines, the long lines where the field is strong, seem to wander around a lot and angle. I was just wondering if you
there is this caveat, and I appreciate you pointing this. Here what we're talking about the plane of sky perturbation of magnetic field. And this is the key here, because your magnetic field in the disk of the galaxy changes in the 3 directions. And the fact that in particular directions you have a plane of the sky magnetic field stronger does not mean that the magnetic field necessarily should be stronger. In fact, we have now ideas how to find this 3-dimensional angle. It's the work in progress, and then we'll have this 3-dimensional magnetic field. But at the same time, I would say that for me, it is encouraging that with our map of magnetic field, we were successful in producing this starlight polarization.
Right. Great, thanks.
Thank you.
So I just want to follow James' question. So do you think that, maybe on large scales that we can say the turbulence and magnetic field in energy computation approximately, but your measurements show that on small scales, their ratio can be highly homogeneous?
Yes, we see significant variations of magnetic field, both in direction and at least perpendicular component of magnetization. So I'm not sure that I understood your question, to tell the truth.
Yeah, I'm just wondering because this MA values are very important for modeling cosmic rays and star formation, as you mentioned. So, and I see a big variations of MA in with space. So does it mean that we cannot simply just assume MA is approximately equal to 1 everywhere when we consider?
Definitely MA is not equal to 1 everywhere. And just look at this iron picture. Look, this is MA distribution that we obtained for serpents. It's changing significantly, as you see. And it's, in fact, changing over significant range. So no, it's not, definitely not fixed single value.
Okay, so another question is, have you considered to apply this technique to measuring high redshift magnetic fields in the cosmic large-scale structure, like in high redshift galaxies? And what would be the advantage compared to polarization and rotation measures by SKA, for example?
Well, when we have SKA, we definitely can use it. The technique requires resolution. We are averaging over to obtain each of our gradient directions. We are averaging over sub block. And this sub-block, just experimentally, we find should be more than 10 pixels in one direction. So it's we need to downgrade the image to obtain the statistics, reliable statistics. For obtaining these directions, and therefore we need to get the high quality, high resolution images. I'm not aware of any high resolution images of the high redshifted galaxies that are available at the moment. With SKA, this should be available, and indeed it will have multiple applications there, but not at the moment. The best we have is this ALMA measurements of nearby galaxies, and I showed one of the images, and we obtained magnetic fields with high resolution compared to Hawk plus polarization.
Thank you. Other questions?
Can I ask one more question?
Sure.
Yeah, so I understand the argument that the velocity gradient, it would be perpendicular to the B field bundle. Well, is that also, so the velocity, there will be also other places where you have large velocity gradient, like shocks. So, but the shocks may not be corresponding to kind of your magnetic bundle lines at all. There could be local motion driven by other things. So is this velocity gradient affected by some of these shocks where we know there are shocks?
Definitely, there is effect of distortions. There are large-scale distortions, for example, coming from galactic shear or other shears, but they are negligible because I explained to you that the gradients at the smaller scales are most important.
Yeah.
For the shocks, it's a bit funnier because shocks, and we proved this with numerical simulations, are affecting really very localized regions in terms of velocity. In terms of density, they are important, and they change the density gradients. But as soon as we have this averaging over the area, for example, 10 over 10 or 20 over 20, in this case, the contribution of the shocks, although important over the line, is becoming subdominant over the area. So
Yeah.
this is what we found, and therefore comparing the density and velocity gradients, we can easily identify shocks, which we proved with numerical simulations.
Yes, thanks.
So if there are no other questions, thank you very much, Alex.